In this video, we're going to explore how to use epidemic modeling, more specifically the SIR model, to measure the spread of an infectious disease. Whenever a new virus appears, whether it's a common cold or something much more serious such as COVID-19, scientists rely on these types of tools to answer key questions such as how quickly will the virus spread? How many people will be affected by this new disease? Or are there new things we can do to stop or slow down the outbreak of this disease? The SIR model, which is short for the Susceptible Infectious Recovered model, places each person in a population into one of the following three groups. A person is either susceptible, meaning they haven't had the disease yet, but they might get it. They're infected. These are the people who currently have the disease, and they are considered contagious, being able to pass on the disease to others. And then there's the recovered removed compartment. While this is a fairly simple model, it serves as the foundation for more complex models used by government organizations to monitor and analyze infectious diseases. We're going to start out with a very simple case of only 20 people. Let's assume that 1 out of the 20 people in our population are infected with the disease. So that means that there are 19 healthy, susceptible people, and there's 1 person that is sick on day 1 of this study. Notice that we use the subscripts S1 and I1 to represent that is the day that we are working on. This 1 person will move around in the population, and as he moves around, other people will also get infected with this disease. So now on day 2, if you look, we have S with a subscript of 2, meaning the number of susceptible on day 2 is reduced to 17, while the number of infected has grown from 1 to 3. And as these 3 infected people move around the population, even more people will become infected with this disease. As we know, with any infectious disease, as a common cold or COVID, people eventually move from the infected compartment to the recovered compartment. So let's assume our initial person who's been sick for 2 days has now recovered and is no longer infectious. That leaves us with our day 3 model with 13 susceptible on day 3, 6 infected on day 3, and 1 recovered on day 3. So how do we create equations that help us predict how people will move from one group to the other? First of all, let's think about how people move from the susceptible to the infected compartment. The key variable we need to know in order to determine how many people move from the susceptible to the infected compartments is called the transmission rate. We can really think about beta, or the transmission rate, as the expected number of susceptible people that each infected person will infect per day. S is the number of people in the susceptible compartment. Now, if you think about this, if there's a large number of people in the susceptible compartment, we would expect more people to move from the susceptible to the infected each day. The last part of this equation, I over N, is the number of people in the infected compartment divided by N, which is our population size. So it's the proportion of infected people in our population. If there's a lot of sick people in the population, they're going to be infecting more people than if there was just 1 person in the population. Thus, when a larger proportion of the population is infected, we would expect more people to move into the infected compartment the next day. We also need to measure how do people move from the infected compartment to the recovered compartment. The variable we use to measure that is called the recovery rate, represented by gamma. So when gamma is large, more people will move from the infected compartment to the recovered compartment. Of course, this also depends on the number of infected. So this equation simply tells us the proportion of the infected people who will be recovered the next day.